let's make the best of it. I hope everyone and their families are staying healthy. And so today and this week, I'll be talking about gravitational waves, both their detection and using them to look for new physics beyond the standard model, and also gravitational wave sources from the local universe. This is in contrast to the other series on gravitational waves this week, which is more focused both on the theory of gravitational waves, as you heard this morning, and also detection from the early universe, cosmological gravitational waves. Here we'll be focusing on quote unquote local gravitational wave sources, and we'll see what that means as time goes on. So, and since we're not in person, I can't see who's confused or falling asleep or whatever. So please, let's try to make this as interactive as possible and ask questions in the chat, or just ask directly if you have a question, so that we can make this a bit more interactive. Okay, so without further ado, the story of gravitational waves, at least as we see them today, began 1.3 billion years ago, when two 30 solar mass black holes in a faraway galaxy merged and produced a huge burst of gravitational wave radiation. So here is a visualization of that merger. This is a real numerical simulation. Here, what's shown is a 2D slice of our universe as it would be seen from a higher dimensional universe with the two black holes merging. I think last week you heard a bit about extra dimensions and things like that. This is just a visualization tool in this case of how the world sheet of our universe would appear from a higher dimension. You can see that there's a large amount of curvature around where the black holes are, and the colors represent the slowing down of time relative to an observer at infinity. Here, they just slow down the video at the merger to show you how the space is really very extremely curved at the point where the two black holes come together. And you can also see that there's a lot of fluctuations, and then at some point everything settles down as the two black holes merge into one, and the gravitational waves travel outward to infinity. The amazing thing here is that this is a really huge amount of energy that's released in the gravitational waves, and there's a lot of these. I'll put these links in the notes afterwards. There's a lot of really cool animations that are made by this project and other ones on the LIGO website that are doing accurate numerical calculations of these events. So 1.3 billion years later, these gravitational waves reached Earth, and they traveled through the LIGO detectors. And this is how the cleaned up data looks like in the LIGO detector. So on September 14th, for the first time, LIGO observed gravitational waves from the merger of these two black holes. And this event was incredibly powerful. It released over 50 times the amount of energy as there is, or power as there is all the stars are radiating in the universe today at the same time. However, the impact it had on the detector is really tiny. So what's shown on the y-axis here is the strain, which is the change in the distance of the arms of the LIGO interferometer. The fractional change, it's about 1 part in 10 to the 21 as a function of time. And you can see that in the two detectors, one which is in Hanford, Washington, and one which is in Livingston, Louisiana, the strain as a function of time looks the same once you take into account the time delay between the two locations. And this is a really magnificent confirmation of the theory of gravitational wave radiation. It's exactly the kind of waveform we expect to see from these kinds of mergers, and it shows up in the two detectors at the same time. But it's a really, really tiny effect, and we'll talk about why it's so tiny and how you can hope to detect it in the next hours. Another fun way of looking at it is a lot of the LIGO group really like to describe this as opening a new window on the universe, which is totally a true statement. We have never been able to observe these kinds of events before, but another analogy is that in addition to usually being able to observe electromagnetic radiation and see all of the astrophysical occurrences throughout space and time, now we're also able to quote unquote hear the universe. And here we're plotting the frequency here as a function of time. You can see, in addition to the waveforms that are shown here, you also have these frequency versus time plots where you can see as the black holes merge and the signal gets more intense, it also goes up in frequency. And you can, and this frequency happens to actually be in the audible range of the human ear. So if your eardrums was able to detect a fluctuation of 1 part in 10 to the 21, then you could hear those gravitational waves yourself and you wouldn't need the LIGO detector. So you can actually hear, if you listen, I think this works, you can hear what these gravitational waves would sound like. So the low frequency rumble is the background noise, and then you hear the chirp at the end. The whoop, whoop is the chirp of the gravitational waves that are merging. And they did, the people who made this audio from LIGO upsampled it to higher frequencies so that you can hear it better. That's why there were two different pitches. But yeah. So this is how you would hear that there were two black holes that merged a billion years away. You had really, really sensitive ears. So for now, we have to rely on LIGO. I mean, that's very exciting. There's a revolution in physics because there was this new detection. This is a bunch of us in Perimeter Institute, where I was at the time when the detection was announced in 2016. We all came down to the cafeteria to watch the announcement. But this is, you might ask, well, Perimeter Institute is a theoretical physics institute. Why are we also excited about the fact that gravitational waves have been detected, beyond just the general amazement at the progress of science? And so that's what I'll be focusing on, is what we can do with gravitational waves and how this progress is helping us also push particle theory and progress in particle physics. Of course, the first point is still stands. It's an amazing scientific and technological achievement. So that's something in and of itself. In addition to that, these discoveries have already taught us several things. First, they confirm what we predict about the strong gravity regime in general relativity, which has not previously been observed. And we're already learning a lot of new things about the most extreme objects in our universe, black holes and neutron stars. And but finally, we have this new way of measuring things that we didn't have before, and we can use this as a new tool to study different kinds of physics. So let's go through these points in a bit more detail. You've probably seen these pictures before, but on the left is one of the LIGO interferometers. It's a 4-kilometer long Michelson interferometer, which can measure displacements, as I said, to better than 1 part in 10 to the 21. And on the right is one of the test masses, one of the mirrors that's used to measure these displacements. It's a several tens of kilograms, beautifully crafted mirror that is suspended on a series of suspensions to reduce the noise in the detector. And this whole enterprise took several decades and a team of many physicists, in addition to having really complex optics and laser systems and vacuum systems and suspension systems, there was also huge international collaboration, which is very cool. If you look closely, I'm over here. I actually worked on LIGO as a summer student like a while ago when I was an undergrad, and I only broke one capacitor, so I didn't mess up the progress of science. So what have we learned so far? Just in terms of what we know about astrophysical objects that we didn't know before. Since the first detection, which is the merger of two 30 solar mass black holes, LIGO has seen more than a dozen black hole mergers, as well as two neutron star mergers. So those are shown here. The purple dots, so this is just showing all of the black holes and neutron stars that we've measured so far. The purple ones are the ones that we inferred previously from electromagnetic observations. The yellow neutron stars are also the ones we've inferred from electromagnetic observations. The mass is increasing as you go up. Now the blue are all of the new systems, like two black holes merging into a heavier black hole that LIGO has observed, or two neutron stars merging into a heavier object, which we're actually not sure if it ends up as a neutron star or as a black hole. So that's an interesting physical question. A recent event has been quite surprising in that it was a very heavy, relatively heavy black hole of 20 solar masses and 2.5 solar mass object, which according to current stellar evolution models and so on, is both too heavy to be a neutron star and too light to be a black hole. So that's already teaching us something interesting that we didn't expect before from these kinds of objects. And of course, we've also observed the neutron star merger in light waves as well as gravitational waves. So here on the left is the gravitational wave modeling of the neutron star merger, and on the right is the visualization of all the matter and light around the neutron stars as they merge, and a concurrent observation of the gravitational waves and the light waves enabled us to learn more about the equation of state of neutron stars and also about the formation of very heavy elements in these types of mergers. And it's very exciting that this is just the beginning of a new field. So far, we have observed all of this with just 3 detectors, LIGO, 2 LIGOs and a Virgo in Italy. But there's observatories that are currently being constructed and planned around the world. And in the next decade, here we're showing the different observing runs, which will increase in sensitivity. So this is just showing how far a interferometer is expected to see a neutron star merger in megaparsecs. From the current run, which we're finishing up run 3 right now, or LIGO is finishing up run 3 right now, and Virgo, and other observatories are hoping to join and continue improving the sensitivity as well as the coverage across the globe. Beyond the existing interferometers, there's also plans to continue improving. So here is something that we'll see a few times later on, is the sensitivity of the detector is plotted on the y-axis as a function of frequency. So the current run is shown here in gray, and there's plans to continue improving the sensitivity to get to smaller and smaller gravitational wave amplitudes with future generation detectors that will be even longer and use enhancements in quantum optics and mirrors to really push toward more sensitive, more sensitivity. And the cool thing about these ones is that aside from all the other physics that we can do, I think it's just an amazing fact that the future detectors will be able to see all of the black hole and neutron star mergers in the observable universe that have ever happened, because the reach will be to large enough redshifts that by the time that the black holes, as the universe evolves, stars form and then they form black holes or neutron stars. By the time that happens, you're at low enough redshifts that these future observatories will be able to see these mergers. So that's just a very impressive map of the entire universe. It's not something we can ever see in any other way. So seeing these black holes merging at redshifts of 6 or 10 will really teach us a lot about astrophysics, stellar evolution, and maybe some other things as well. So the future is very exciting. What can we do with it? So there's a huge range of science opportunities, some of which LIGO is already taking into account, and some of which, and there's more to explore. So I encourage all of you to think of new ideas of what you can do with these detectors. But just to give some examples, you're going to be hearing a lot about stochastic gravitational waves from the early universe and other physics, other beyond the standard model physics. Of course, there's more information that we'll get about, for example, neutron star equations of state, what happens after the merger of the neutron star, tests of general relativity. You can use some of these events to infer distances and cosmological distances that can help you measure other properties of our local universe. But you can also see some stuff on here that may be surprising, like continuous waves from axions, or other beyond the standard model tests. And we'll get into that in the later lectures. So there's a whole range of stuff that you can do with these gravitational wave detectors. And beyond, so I've been focusing on LIGO because that's the observatory that has detected gravitational waves. But beyond LIGO, there's a huge range of frequencies, from high frequencies going to lower frequencies, that's planned or ongoing observations of gravitational waves at other wavelengths. For example, LISA is a future observatory that's already undergoing some prototype testing that will measure gravitational waves at wavelengths about 1,000 to 1,000,000. The frequency of LIGO, there's ongoing measurements of pulsars, which act as clocks to tell us about gravitational waves at frequencies whose wavelength is of order in inverse year. And of course, there's already constraints on gravitational waves from CMB physics. So I'm happy to talk about these more. I'll talk a little bit about the pulsar timing array tomorrow in the context of dark matter searches. But if any of you are interested in hearing more, can let me know and I can include a few things in the future lectures. So any questions on just general LIGO?
There is one question by Nehal Mittal. He asks, how does one calculate how much energy power gravitational waves carry? Is there a similar procedure to calculate the momentum associated to them?
Yes, good question. We will potentially get there today, but it's one way you can think about it, just as a quick answer, is that in analogy to electromagnetism, you can calculate the power that is carried by an electromagnetic wave. It's proportional to the amplitude of the wave squared. Similarly, in gravitational waves, you can also calculate the power that's carried by gravitational waves, and it's proportional to the amplitude, which is the strain of the wave squared. But I'll go into more detail about that later as well. And I think on the exercises, there's an exercise where you're supposed to estimate the power of gravitational waves that were purported to be detected in the 60s. So you'll get to try out doing that yourself. Let me know if you have questions.
I don't see any more questions now, so I guess you can go on.
Okay. And so just to let you know what the plan is, so today I'll be focusing on a little bit more about the history of gravitational waves and their detection. You guys have 4 lectures today, so I thought we would take it a little bit easy and do a bit more background. And then I'll get into calculating gravitational waves from some example sources, how to detect them, and what are the main noise sources in LIGO. Depending on how much time we have, that might carry over into tomorrow. And then I also talk about using these tools of gravitational wave astronomy to look for beyond the standard model physics, in particular light, dark matter. And there's a couple of ideas out there about how to look for these kinds of dark matter searches, how to do these kinds of dark matter searches with long frequency, long wavelength, low frequency gravitational wave detectors. And that will get us a little bit warmed up about thinking about scalar fields and in the context of general relativity and gravitational waves. And we'll also talk about how to look for scalar fields, light scalar fields or light vector fields using black holes and gravitational waves. We'll see that in the presence of very light new particles that are predicted by models beyond the standard model, which you may be hearing about in your other lectures, for example, axions that solve the strong CP problem of the standard model. These can be looked for in gravitational waves. So here is a sneak preview. There's a cloud of axions in purple around a black hole, and over time it emits gravitational wave radiation that then can be detected in the LIGO detector and is currently being searched for in some of the ongoing gravitational wave programs. Okay, so that's the plan. Let's get started for today. First, as I said, I want to just give you a bit of a flavor of how we got here. As in relation to the question that was asked, you can think of gravitational waves, and they've been thought of this as this for a long time, as kind of an analog of electromagnetic waves. So we know electromagnetic waves, as they propagate, cause a displacement of charged particles. Gravitational waves cause a displacement of matter. And since Maxwell first formulated his theory of the electromagnetic field, where he realized that electromagnetic waves travel at the speed of light, he started already wondering whether you have a similar situation for gravitational waves, since both gravity and electromagnetism in the static limit have 1/r potentials. And if you postulate that information has to be carried at finite speed, then you might expect gravitational waves to propagate as electromagnetic waves propagate. Of course, this was just words at that level, but it became more robust when Einstein postulated his theory of general relativity in 1915 and predicted gravitational waves. In the year later, he also was able to calculate the energy loss to gravitational waves, which is the power to gravitational waves. But Einstein himself was very confused about whether gravitational waves are actually a coordinate or artifact or a real physical effect of the theory. And in 20 years after he postulated his first theory, he wrote to his friend Born that he arrived at the result that gravitational waves do not exist physically once you get to higher order in perturbation theory. And he sent this paper off to a journal. I love this story because I guess Einstein did not understand the concept of peer review. He sent his paper to the physical review in June of 36. And the editor got back to him saying, oh, we have a few issues with your manuscript. Do you care to comment on them? And Einstein replied, dear sir, we sent you our manuscript for publication and have not authorized you to show it to specialists before it is printed. And he never published in that journal again, even though later people had shown him that indeed his original statement was an error and gravitational waves do exist. I think this caused a lot of confusion in the field. Perhaps a lot of people had understanding of the physical nature of gravitational waves, but I think it took until another 20 years later at this famous gravitational wave conference in Chapel Hill, where physicist Felix Pirani was presenting a calculation of the physical relative acceleration of static test particles on which gravitational wave is incident. So this was kind of the first really physical calculation of what effect a gravitational wave will have on test particles or matter. And during the questions with his advisor, Bondi, they came up with the idea of either connecting the two masses by a spring or something called the dash pot, which I had no idea what that thing was before, but it's some sort of viscous energy lossy mechanism, so that if the two masses move due to the impact of the gravitational wave, energy will be absorbed, and that's, you know, a hallmark of a physical system is that there's energy transfer. So a lot of people were inspired by this discussion of the physical nature of gravitational waves. Bondi published this sticky bead argument in Nature, and Weber and Wheeler published this rejection of Einstein and Rosen's previous argument of there not being a physical manifestation of gravitational waves. And because Feynman was at that conference and talked about sticky beads, now everyone calls it Feynman's sticky bead argument, because I guess he was able to capture it in a colorful way. But the discussion was really started at this conference. And another participant there who really started the field going was Joe Weber, who was an experimentalist, and he decides that he can, you know, since we know that we can detect that gravitational waves are physical, that means they can be detected, and he decides that he is going to be the person to detect them. An analogy to the two test masses connected by a spring or a dashpot, Weber designs his resonant aluminum bar. So the idea is a gravitational wave passes through and resonates at a given mode of an aluminum bar, and that energy that's dissipated can then be measured. In '69, Weber announced that he had seen gravitational waves. In fact, he'd seen them at coincident detections in different geographical locations for 2 different bars. And this started basically the whole field of gravitational wave astronomy. Unfortunately, all of the excitement didn't lead to any confirmation. Several follow-up experiments only found null results. But these Weber bars are still used to search for broadband gravitational waves at high frequencies. The problem is that you're really only sensitive to gravitational waves that have a frequency that's comparable to the vibrational modes of these bars. So they're very narrow detectors. And in fact, one of the most recently built detectors is nearby where we would have been. It used to be based in Sao Paulo, but it got moved to this National Institute for Space Research. And most of the group that's working on it has now shifted to LIGO, but it's still in progress, and these bars might be better suited to certain types of signal detection than the interferometers that I'll be focusing on for the rest of the talk. And just to give you a sense for the future, the detections that Weber announced were corresponding to a strain of about 10 to the minus 16. So keep that number in mind for later, but this is the sensitivity that he was able to achieve. Of course, the bars of today, like this Maria Schoenberg one, achieved much better sensitivity, but 10 to the minus 16 was already very impressive at the time, but we'll see that that's not really sufficient to have been expecting a gravitational wave signal. That's not really sufficient sensitivity to have detected a gravitational wave signal at the time. So perhaps it was not surprising that these detections were not confirmed. Now, of course, as having been born in the Soviet Union, I'm obligated to say that laser interferometers were first proposed by a Soviet physicist in '62. There's a paper by Gerstenstein and Pustovit, which was published in Russian in '62 and an English translation in '63 that proposed using laser interferometers to detect gravitational waves. But this idea didn't take off in the West until Ray Weiss at MIT proposed this laser interferometer after getting into GR while teaching a class where he had to catch up with the students and brainstorming about how you would actually try to detect the physical nature of these gravitational waves. And in a sense, using an interferometer for gravitational wave detectors is a really beautiful manifestation of the classic thought experiments in general relativity, starting from Einstein when he talked about traveling on a beam of light. Everything that's measured in relativity is often measured in thought experiments by sending light pulses from one place to another. And in the original Pirani paper, he also talked about an observer inferring the distance between these two accelerating masses by sending light signals between them. So this is really taking that theoretical concept and putting it into a real experiment. And you can see on the right here, on the right here is this diagram that was proposed by Ray Weiss in '72 in this note that he never bothered to publish, which basically included a lot of the experimental design and noise sources that go into interferometer detection today. Of course, in the meantime, so this is all very abstract. So far, we think there should be gravitational waves, but we think they should be physical. But there was more excitement in the '70s and '80s because this is the first time where it was realized that gravitational waves can actually have significant impact on systems. Hulse and Taylor discovered what's called the binary pulsar system, where you have 2 neutron stars, and one of them is a pulsar, which is a star that emits very beamed radio waves toward one direction, and as it rotates, that beam sweeps across, and you can measure the frequency very precisely. It turns out that these pulsars are quite precise clocks. As I mentioned, they're also used in their own way for gravitational wave detection. But these pulsars are very precise clocks, and so the fact that one of the two bodies in this orbital system was a pulsar permitted Hudson-Taylor to measure the orbital period very precisely. And they measured it over time, and they found that the orbital period decayed exactly in accordance with the predictions of general relativity. So as these two bodies orbited each other, they emitted gravitational wave radiation that lost energy exactly at the rate predicted. As you can see in this plot here, here's the shift in the fractional orbital time, say, as a function of time. The line is the GR prediction, and the points with error bars are the measurement. This is later data that's taken through 2005, but in the original measurement was more at the tens of percent level, but it still agreed very well with GR. And 15 years later, they got the Nobel Prize for this observation. So at this point, people kind of are certain that gravitational wave radiation exists, and we just have to detect it. The LIGO collaboration was founded in the early 90s, and initial LIGO ran for about 10 years in the early 2000s at sensitivities that were not really expected to reach the well-motivated astrophysical targets, but which nevertheless really achieved impressive improvements in technology and strain sensitivity. And then advanced LIGO started running about 10 years ago, and 5 years ago, they finally reached the sensitivity, or advanced LIGO started getting built about 10 years ago. 5 years ago, it started running, and almost immediately, they reached the sensitivity necessary to see these gravitational wave mergers. So that's 100 years from the formulation of general relativity, and nearly 50 years after the first claimed detection by Weber, we have a confirmed detection of gravitational waves from this black hole merger. Comments or questions?
There is one question. By Martin, he says, I know that LISA or ELISA is a near future experiment. Is PTA another experiment, right? Do you know what is the status? Could you talk about this experiment a little more?
Yeah, there are several collaborations, including PTA, which stands for Pulsar Timing Array, around the world. And basically what they do is they observe pulsars, like the one in the Hudson-Taylor binary. They observe pulsar timing very accurately over time. And these pulsars, which are located throughout our galaxy, are basically very precise clocks that you can compare with each other and with clocks on Earth to see whether there is variation in their pulsation time over time. And if there is a variation that's, say, periodic and is correlated across many pulsars, that can correspond to a gravitational wave which is passing through and changing the relative metric at the pulsars compared to on Earth. And so this is already ongoing. They're reaching sensitivities where they might expect to start seeing something from, say, a stochastic background of supermassive black holes. But so far there are no signals, yeah, so far there's no significant signals. But I'll talk about it also a little bit more tomorrow as well.
There is a question by Jarek. He says, Gravity Probe B has confirmed GEM approximation, which also already has gravitational waves. What is the status of confirmation of higher GR terms?
Sorry, I didn't understand the beginning of the question. Gravity
So
probe be what?
gravity has confirmed GEM. I don't know what GEM, maybe, yeah, approximation. I don't know what GEM approximation is, which also
Yeah, I
already
can see
has
there.
gravitational waves. What is the status?
Yeah, so, well, as far as I know, all of the tests done so far confirm general relativity to the level of precision that we can confirm it. So there are some calculations that, for example, when you are looking at mergers and so on, you do an expansion in post-Newtonian parameters or in other parameters, and you compare that to what you compare what you predict to what's observed, allowing some of those parameters to vary. So far, all of those tests are consistent with confirming GR. I'm not sure if that answers your question, but it's also very difficult to write down deviations of general relativistic models which have which are consistent with the growing list of observations and can still give you new signals in these types of mergers, but you never know.
Okay. Felipe asks, what are the restrictions on a source of gravity waves? What kind of source will produce a measurable gravity wave?
Good. So we'll get into that, but basically the best sources are very massive, very relativistic, and very close. Good.
Okay. Don't see any more questions, so please go.
Okay. So to get into the question that was just asked, let's talk about what kind of signals are generated from gravitational, what kinds of systems generate gravitational waves. You heard about this morning, these are slides I stole from Daniel, about the definition of gravitational waves. And you saw that from the constraints of general relativity, you can show that there's only two degrees of freedom that are propagating, and they can be parameterized in these two polarizations, which we call H plus and H cross. There are 2 degrees of freedom that for massless gravitational waves that can propagate, and they correspond to transverse distortions of space-time. Transverse, where I say transverse, meaning transverse to the direction of propagation of the wave. So what's the typical amplitude of these gravitational waves? How do you detect one? Let's go. Can you see the notes here?
Yes.
Okay. So let's talk about that in more detail. So gravitational waves from local sources is what we'll be talking about. And let's consider a small perturbation, which is propagating in vacuum. So we expand the usual metric as Minkowski and a small perturbation where its magnitude is much less than 1. Also, I realize my handwriting is not perfect, so please let me know if you can't read something. And we're studying solutions to the wave equation, box h mu equals 0, where it's propagating through free space with no sources. Just like as in electromagnetism, you can find solutions to the wave equation by integrating over the source. So you heard today about Einstein's equation and how the stress energy tensor and the gravitational tensor correspond are equated to one another. through 10 differential equations. And then the linearized regime with a source, you can find the strain of gravitational waves as follows. So T mu nu is the stress energy tensor evaluated at some point in space and time, integrated over the source. And I'll probably be dropping C's randomly, but I usually keep G Newton because it's very confusing to me when people don't keep G Newton. I think a particle physicist is someone who sets C to 1, but G Newton that keeps G Newton, and a general relativist is someone who sets both to 1, and then all of the units are just the same. So in the non-relativistic limit, this expression reduces to something called the quadrupole formula. So the spatial components of the strain, gravitational wave strain H, are just given by G Newton. So everything is proportional to the coupling gravity times this quadrupole, second derivative of the quadrupole moment. So this is a quadrupole formula. And what is the quadrupole moment? It's given by this transverse traceless combination of just what you expect, the integral over the energy density weighed by the quadrupole displacement x. So this is an analogy to the dipole moment in ENM or the quadrupole moment in ENM, where you're looking at the quadrupole moment of the charge density. Here you have the quadrupole moment of the energy density rho. And unlike in ENM, there's no dipole, term. So let's estimate the strain from a typical system. Oops. What is possible strain? So let's take two objects that are orbiting one another with orbital angular frequency omega at a radius r. And let's take both of them to have mass m. Let's say these are non-relativistic or only mildly relativistic, and this will not be exactly true later on, but good enough for us just to have an estimate. So from Kepler, we have that the orbital angular frequency omega is g times the sum of the masses over r cubed in this case. So this is just 2gm over r cubed. And let's calculate what the strain for the system is, and then we'll see what which kinds of systems give you the biggest types of strain, biggest strain amplitudes. Does anyone have intuition about what the scaling of the strain will be for this type of orbital system? You can put out some guesses if you like while I'm doing the calculation. So you can do this in more detail later if you're interested, but just to do a quick estimate, the energy density here, you can just consider as a delta function times the mass, delta function at 2 positions in X and Y for the 2 masses. And let's say they're undergoing circular motion, so that the coordinates are just changing in time as they're going around the circle of radius r, which is just given by cosine theta, sine theta, and the corresponding for the second mass, where theta is the orbital frequency times time times some phase if you like, but that doesn't affect the amplitude. So if we plug in this energy density into the X component of the quadrupole moment, you get something that's of order mr squared 1 plus cosine 2 omega t, which is what you'd expect. Is proportional to the square of the separation and the mass. So like we said before, the heavier and the closer the objects are, the better. And the time derivative, just at the order of magnitude level, let's say all of the components are about the same. Of course, some of them will be 0, depending on the X, Y, or Z components. But all of them have the same order of magnitude. So this is order second time derivative of X component, which just brings down more omegas. And if you go back to our quadrupole formula for the strain, it's about 2g over r times the second time derivative, which in this case is 2gm r squared omega squared over r cosine 2 omega t. Again, you should have very good intuition from this from say electromagnetism, because there the amplitude of the wave is also proportional to say the dipole moment and the charge. Here the charge is given by the mass times Newton's constant effectively. So can we plug in some numbers here just to get a rough sense of what kinds of strains we can expect? Let's say you have 2 black holes, which are the densest things you can possibly get. Then we have that their separation is at most, or at least, I should say, the size of the black hole, which is g Newton times m. So this is for a Schwarzschild black hole, its radius is 2gm. For a Kerr black hole, its radius is g times m. So let's take r is approximately gm. And if they're very close to merging, then the orbital frequency is very fast. We had before that omega squared is gm over r cubed. So if all of the scales are at the, if they're about to merge and all of the scales are at the size of the black hole, this is about 1 over RG, where RG is the black hole size. So if we put all that together, we get that the strain on dropping all of the coefficients is GM gives you an RG, the orbital distance gives you RG squared, and the orbital period gives you an over RG squared divided by the distance. So it's basically the horizon size divided by how far away the system is away from us. For a typical black hole, that's say a few solar masses, the horizon size is 10 kilometers, and some of the events that we're currently observing are at a distance of 100 megaparsecs. So if you estimate what that number is, it's about 3 times 10 to the minus 21. So some of the most violent events in the universe where you have two black holes and you smash them together are still only producing strains that are less than 1 part in 10 to the 20, which is why you need extremely sensitive detection techniques to try to observe them. And I encourage you to try to, this is not a hard calculation, it's mostly classical mechanics. So if you want to work it out more carefully for elliptic orbits or different masses, then that's also good, good exercise for building intuition. So any questions?
Yes. So Ish asks, from the gravitational wave signal, how can we determine the source?
That's a great question. It is not trivial. So basically, for the gravitational wave signal, all that you're seeing is a waveform, which is a strain as a function of time. And sorry, 1 second. Okay. Which is a strain as a function of time. So, for example, if you have two bodies that are orbiting each other early on, you only see everything is basically approximated as a sine wave because the period is not changing, or for a rotating orbit, all that you're seeing is just a sine wave over time, like this. Now, the LIGO analysis takes lots of things into account. For example, how is the frequency changing? What is the frequency? How is it changing as a function of time? And different moments of that. So at leading order, what you can tell is what is the total mass of the system and how fast it's orbiting. And at higher orders, you can tell, for example, is there any precession in the system? Is there a spin of the black holes in the system? And so on. But I can, so I'm not sure if that answers your question, but basically you can't, so from the waveform, you can't necessarily tell what kind of object it is. You can just tell what its mass is, but one example is that LIGO saw a system of neutron stars merging, right? And all they see is that there's some gravitational wave strain that's being emitted over time. However, the frequency at the moment of merger is too high to fit into the gravitational wave band of LIGO itself. So all they can really tell is that there's two very light objects that they came together. They can't see the fact that the neutron stars actually smashed into each other. So there are actually papers written that said, well, LIGO can't actually tell whether this is a neutron star or a black hole because from just the gravitational wave information, all you know is that the object has a certain mass and is smaller than a certain size, because if it was less compact, then you would see the merger in the frequency band of the detector. So in principle, you can't exclude it being two black holes or a black hole and a neutron star just from the gravitational wave information. and you need to rely on other observables like the fact that there were electromagnetic waves that accompanied it to tell you something about the fact that it's a neutron star.
Okay, there is a question from Bruna Lorani. Gravity wave could be used now or in the future to test the hypothesis of the formation of supermassive black holes by the merging of smaller black holes?
So I'm not sure. I mean, yes, in principle, in the future, as I said, some of these detectors will see the mergers of small black holes all the way to the beginning of time. So if your model is that, you know, stellar mass black holes somehow merge very rapidly and make bigger black holes that then form the seeds of supermassive black holes, that could potentially be tested. I think that is thought to not be a viable formation mechanism for supermassive black holes. But the other limitation is that LIGO is only sensitive to a certain range of frequencies, as we'll see later. So they can't see kind of intermediate mass black holes merging. They can see them earlier on. So you might need a wider range of frequencies and detectors to probe those, probe some of those hypotheses.
Okay. Ganesh asks that I double dot in quadruple formula is derivative with respect to time.
Correct.
Okay. Jarek say, isn't the gravito-electromagnetic approximation? I thought it was standard. It was originally introduced by Heaviside in 1893. I don't know. To understand that.
Yes. I mean, there is a way. I think maybe Daniel talked about it a little bit too. But basically, you can formulate some of the GR equations in terms of analogs with electromagnetism, and you can define like a gravitomagnetic field and gravity-electric field and work with those. And sometimes that gives you better intuition for things. And I think you are correct that Heaviside mentioned this kind of in response to Maxwell's first question of like whether you can have gravitational waves and analog to electromagnetic waves. He kind of started writing that down. But whether that's a useful calculational tool or not kind of depends on the problem that we're treating.
Jenny asks, the speed of propagation of gravity waves is always less than the speed of light. How do they measure the speed of propagation of gravity waves?
Good. So in general relativity, the speed of gravitational waves is equal to the speed of light. Exactly. One way that you can test this is from some of these detections. For example, you have this neutron star merger. It emits gravitational waves and it also emits electromagnetic waves. And then you look at both of them and you ask what's the time differential between their arrival, assuming some model of when the light was emitted or even just a general statement. And I don't remember the number off the top of my head, but basically they've arrived very close together, especially given the very long distances that they traveled. So you can say that at least phenomenologically, the speed of propagation of gravitational waves is equal to the speed of propagation of light up to a certain fractional, up to a certain fractional value. And I can get you the number for next time.
Nehal Mittal asks if you can define the strain. What the strain is.
If I can define what the strain is, well, Yes, I guess. I mean, let's see. So the way that I'm defining it here is just as a small expansion parameter around the background metric. So we're looking at small fluctuations around Minkowski, and you just expand the metric in small parameters around eta, around Minkowski space. So that's kind of what I'm taking as my definition. And then we showed earlier, or I should say Daniel showed earlier, that by imposing some of the freedoms of general relativity, you can show different properties of what the strain tensor, like it's symmetric and transverse traceless and things like that. Observationally, that's what we're going to do next, is show what effect a strain has on objects in terms of measurement. And basically that is the strain is going to be of order of the change of a distance, a fractional change in distance in between free falling objects. But the current definition that I was working with is just the expansion around a background metric.
Okay, there is just one more question by Felipe, which asked if the emission of gravitational waves and electromagnetic waves occur at the same time on the neutron star merger.
Not quite. I mean, yeah, it's a complicated process in the neutron star merger. Basically, you start with very little electromagnetic waves as the neutron stars are inspiraling, and you're just emitting gravitational waves, which is bringing the orbit closer together. And then as the neutron stars start to get tidally disrupted, you start releasing a lot of binding energy, as well as radioactive energy, and that gets emitted as electromagnetic radiation. And there's complicated light curves that follow the merger and the production of the new object, which then fall off over weeks or months that were observed in various telescopes. So the direct comparison of like a particular moment in time when things are emitted is a little tricky, but you can either take something very conservative and say, you know, they were emitted between here and here, or you can kind of find the moment at which the merger occurs, and you can pinpoint where that corresponds to the gravitational wave emission or a particular type of electromagnetic emission. I'm assuming this is related to the question of the speed of the two waves. So.
Still with respect to the previous question, is that perturbed metric is called strain?
Yes.
Okay.
It's the perturbed, yeah, so this is the metric. Let's just be very explicit. This is background metric, which we're taking to be Minkowski. And this is this. So yeah, strain is a little bit sloppy. I mean, this is the perturbed metric, but sometimes when people say strain, they mean the amplitude of this, or maybe they mean the tensor. If you're confused when I'm being sloppy about the language, let me know. I'll clarify, please. Okay.
All right. Wait, another question.
Yeah, please. This is fun. Good.
So Bruno asks, does the collision of two charged black holes also generate electromagnetic waves?
Yes. Definitely. If you have charges moving around, they'll generate electromagnetic waves. The question is more whether you expect charged black holes. So the equivalent charge of a black hole compared to its kind of gravitational charge is usually very small because there's a lot of free charges in the universe. And if you start building up a significant charge inside the black hole, it will easily get neutralized by free electrons or ions in the space around it. So typically you don't expect the charge of a black hole to have a significant impact on its dynamics compared to its mass. But in principle, if you construct such an object, then yes, you can have also emission, just dipole emission of electromagnetic radiation from the orbit as well.
All right. Don't see more questions, so free to go.
Okay, great. So in the last 15 minutes, right? Can't hear you.
Yes.
I'll assume that's correct.
So yeah, we're 19 since we started it late.
Okay, sounds good. So now that we have kind of a goal of what we want to measure, remember it's of order 10 to the minus 21. I want to talk about two things, and maybe the second thing we'll go over into tomorrow. One is what effect the strain actually has in a detector, and two, what are the main things that are stopping us from detecting it, i.e. what is the leading sources of noise in a gravitational wave detector. So let's consider a plane gravitational wave propagating in X direction. Then, oops, then the metric perturbation or the strain will be given by, as discussed already, two components, two polarizations. So can parameterize it like this. So it's transverse in the direction of propagation, and they have 2 degrees of freedom. They're usually labeled as the plus polarization. And the cross polarization. So there's just 2 independent degrees of freedom. And let's say, assume the way that the wave is generated in the system, or just observe it's just produced a single polarization. So let's say the cross component is 0, and the plus component is given by some amplitude. Remember, the amplitude is a dimensionless number times just some periodic function. And they're traveling at the speed of light, so the amplitude of the momentum is the same as the frequency. So let's consider the invariant interval. This is a favorite thing to do in special relativity, between 2 events. For example, 2 free-falling masses through which a gravitational wave is passing. So in the presence of this perturbed metric, the proper distance is given by just plugging in the metric here. Oops, this should be minus. Okay, and let's say we're looking at light travel between them. So this is 0. So let's set up 2 points along, say, the y-axis. This is at minus L over 2. This is at L over 2. And let's calculate how long a light signal that's emitted from one of the masses will take to arrive at the detector here. So we can, so along the y-axis, we can relate the time and spatial components as such. Right? And since we're taking a perturbation where h naught is much smaller than 1, we can take the square root of both sides and expand. The square root gives you a 1/2. And so you find that the time between these 2 points is approximately given by, and we're going from minus L/2 to L/2, it's given by L minus H naught L/2 sine omega t. This is assuming that the time that it takes to travel between the 2 points is much smaller than the period of the wave, so the information becomes trivial. So you can compare this. Oh, sorry, my handwriting is deteriorating. Okay, L minus H naught. So this is in the presence of a gravitational wave. Of course, you can see immediately that if the strain is 0, then delta t without the gravitational wave is just L. So the effective change that the gravitational wave induces is H naught L/2 sine omega t. So we see that for when we're comparing the time travel distance between two geodesics or two free falling masses, it's changed by proportionally to the amplitude of the strain out of frequency of the gravitational wave frequency. And so I like to think about gravitational wave detectors in terms of timekeepers or clocks. So you're always measuring, you know, the time, the difference in time that it takes to get light from one place to another, or you're measuring the rate of time change in one place relative to another. You can also think of this in terms of rods, right? And if you remember back to special relativity, you can have clocks or you can have rods. So you can, if you want to have like a rigid rod that is perfectly rigid, so it's not stretched by gravitational waves, then the distance relative to this rod of the gravitational wave will change proportional to the strain. So you can think of gravitational wave strain as changing all distances by some small fractional amount. That's of order 1 part in 10 to the 20 or less for astrophysical signals. And so what does this look like? Here's another great LEGO video. I really like these. So you have, so one way to measure them is, how do you tell that that this time of flight in this path between two masses is really changing? So let's take the source that we had before is here, and here you have example rest masses, which are the mirrors, and you're comparing the relative distance between the laser in the mirror and the laser in the other mirror. So the light is split in the beam splitter, and it recombines. I don't know why it does that, sorry, but if you take the distances to be equal, then you can set up the interferometer so that the amplitude of the waves coming from the two arms exactly interferes, and you see no signal as shown here. But now if one of the arms changes its distance because, or the time of travel to one of the arms changes because a gravitational wave is passing through, then there will be an interference between the two light paths. And this also has the added benefit because, as briefly mentioned, the two polarizations of the waves have a quadrupolar pattern. So that means that if the wave is stretching one arm, it's shrinking the other arm. So it also enhances, or it keeps the signal while reducing some backgrounds, which are common to both arms. So that's how you're using the light travel of the time of the light travel to determine if a gravitational wave is passing through the interferometer. Now, of course, the actual system is much more complex and it has a lot of controls and different tricks to maximize the signal, but that's kind of the qualitative idea. Any questions?
I see one from Lucas Magno. Is asking, we've been looking at perturbations around the Minkowski background, while at long distances, I'd expect FRW background to be relevant. Are there no effect on the propagation of gravity wave due to the universe expansion?
Good. So here we're really, we've been focusing on just local sources, which are well described by Minkowski, but LIGO is starting to see, for example, sources that are non-trivial redshifts. So, and that's pretty easy to take into account. So if you have a source that's coming from a large enough distance that the redshift in the universe's expansion is actually becoming relevant, then that is going to shift all the frequencies by the corresponding factor. And that leads to actually some degeneracies with masses and things like that. But that can be taken into account in the analysis. But it's just a trivial rescaling of all the scales in the problem.
Yeah, Neil added to this question, is that assumption valid just outside the black hole? The Minkowski one.
It is definitely not valid just outside a black hole, yes. So this is assuming that you're perturbing around a flat space-time, and in these, as you saw in the movie at the beginning, I mean, you can't continuously define space-time to be flat all the way up to the black hole. It's very violently disturbed, and when you're actually doing these calculations to produce these waveforms, you have to typically go into numerical GR calculations where you're going to higher order and taking all of these effects into account numerically. So you can't expand in a small perturbation around some background metric, but you'll have to evolve the full metric. But when we're talking about detection, the waves, remember we have the strain that goes as 1 over r, so it's falling off just because the flux, the power goes as 1 over r squared, so the amplitude of the wave is falling off as you go further away from the source. So by the time we're observing them, you're very much in that approximation. But to actually get the production of the power, you definitely can't do that expansion.
All right, and Anupama Ghosh asks, can you explain again how presence of gravity waves forbids to make interference?
Forbids, yes, right. So, whoopsies. So let's look at this, I guess. So you have, let's consider a gravitational wave which is traveling perpendicular to the plane of the Earth here. It's going into the board, and it has a polarization such that the strain is in the XY direction. So what happens, I'll go back to my notes in a second, but what happens is that the solution of the gravitational wave is that the travel time in the, say, y direction is proportional to the strain times the length of the arm over 2 times some time dependence of the wave, and the time of travel compared to what it would be if there's no gravitational wave. The time of travel in the x direction will have actually the opposite sign. So a wave that was emitted, a light wave that was emitted at the laser at the same time propagates with the same phase in both directions, but it will take, for example, this arm will take the same point in the light wave will take a longer period of time to arrive back and interfere with the original wave. So they'll be out of phase at the time that they re-interfere because of the difference in path travel times. And that will lead to some constructive interference or undestructive interference.
I don't see any more questions.
Okay, so I think I don't want to go into a lot of detail on the next topic because we don't have time. So let me just give you a preview and then we can talk about it tomorrow. So we talked about this gravitational wave strain and how it's generated and how it's detected. And basically, you can think of it as the change in the distance of the arms of an interferometer in this case. But what's stopping us from detecting strains that are as small as possible? Well, of course, in any kind of detector, you have backgrounds and noise sources. You can't just see a arbitrarily tiny signal. And so what a lot of the work in LIGO goes into is looking at how you beat down the noise as much as possible. And here, what's shown here is the frequency. So LIGO is sensitive to frequencies between 10 and hertz and about 10 kilohertz on the x-axis. And here I'm showing the strain noise density. So you, for now, just forget about the per hertz. So it's about the amplitude of the wave that you could see if you observe it for about a second. And you can see there's lots of curves on here, which correspond to different contributions to the noise in the detector. At low frequencies, you can see a bunch of lines that go down very quickly, and these correspond to noise from the mirror, the fact that the mirrors are not free falling masses. Ideally, you would just drop the LIGO mirrors and send light signals between them, but then they would fall on the earth and break, and that would be very sad because they're very expensive. So in a realistic experiment, unless you can go to space like in LISA, you want to, you have to attach the masses somehow to the earth, and this leads to noise because the earth is shaking. There's a lot of seismic vibration, and there's also the supports themselves that the mirrors are hanging on are also vibrating because they're at non-zero temperature. So that's all at low frequencies, and LIGO is going to have a hard time improving on that anymore. I mean, they're working on it, but you're not going to get this much below 10 hertz. But you can see that over most of the frequency range of LIGO, you're dominated by this bucket, which is labeled as quantum. It's the purple line here. And so that's what I'll talk about a bit next time, is where this noise comes from. It's basically from the fact that there's limiting factors, which are called shot noise and radiation pressure, which is the fact that light is made of photons. which come in a finite number, and that introduces an intrinsic limit to how well you can measure the position of a mirror. On one hand, if you have a small number of photons hitting your mirror on average, then sometimes you will misinterpret just a statistical fluctuation in the number of photons as having more or less power, and you'll think that's a gravitational wave causing a change in the interference pattern. On the other hand, if you have a lot of photons hitting your mirror, then they'll push the mirror around and cause the actual physical distances between the mirrors to change, and that can also be attributed to a gravitational wave. So there's a trade-off in how these two noise sources contribute, but they're kind of two aspects of the same thing, and they're basically what's driving the sensitivity of the detector over most of the frequency range. Any questions?
Yeah, there is one question. Why for a particular frequency around 100 Hertz, quantum is given tightest constraint for strain, where the bound relaxes for low and high frequency?
Yeah, so this is related to this trade-off that I'm talking about, and we'll get more quantitative tomorrow, but basically when you go to higher, there's an optimal frequency that's related to the length of the detector and also the amount of laser power, but it'll make a bit more sense once we start writing down some equations. So hold your questions for that.
Martin asked if you can repeat what the quantum noise is.
Yes, so I didn't define it exactly, but it's basically it's a combination of two effects: shot noise and radiation pressure noise. And it's so the two things that are described is the fact that laser is made up of a finite number of photons hitting the mirrors, and that can affect your measurement of the interference pattern.
Okay.
It's not very, I mean, it's quantum in the sense that light is made of photons. There is actually very cool things happening at LIGO where they're using things like quantum squeezing of light to try to bring down these noise levels as well. But this is a very benign sort of quantumness.
Okay. There is one more question. Why for low frequency the bound is very relaxed?
Yeah.
Yeah, I don't know. Yes. Why
yeah. So it's related to these sources of noise, which are seismic, Newtonian, and so on. Basically, well, first of all, the Earth is shaking all of the time, and the frequency spectrum of that is peaked at lower frequencies because the higher frequency oscillations are damped. And you can see that by looking at, maybe I can quickly look at that next time too, is just by looking at a response of a harmonic oscillator. If you shake a harmonic oscillator at very high frequency, the response will get damped very quickly as F over F naught, where the F naught is the natural resonant frequency of squared, sorry, of whereas the natural resonant frequency of the oscillator. And so basically, everything is a bunch of oscillators in the Earth already, and then LIGO is also hanging the mirrors and a bunch of pendula, which are harmonic oscillators, and so they're able to filter out a high frequency noise. If you shake the pendulum at the top at a high frequency, the corresponding motion of the pendulum will be reduced, but you can't do that infinitely, and at some point you hit this wall at low frequencies, which is coming from seismic noise and also the noise in the suspensions themselves.
Okay, probably we should stop here because otherwise we will overlap with the next lecture.
Oh yeah, sounds good.
If there will be more questions, maybe we can just refer to tomorrow or to the Slack channel.
Sounds good.
So
and I'll
thank you
try
very much.
to,
Yes.
yeah, I'll try to start off with the questions that we ended on so that can get those answered.
Okay, thank you, Masha,
Thanks,
for a very nice
guys.
lecture. Thank you.
Okay. Hi, Chaco.
Hi, Rogerio.
How are you?
Good.
So I'm thinking, since I think Masha went a bit late, I'm thinking of starting 5 minutes after, after half an hour, so people can have like 10 minutes to rest a little bit, if that's okay. And then you can finish 5 minutes later also.
Oh, that sounds good, yeah.
So people, you can get 10 minutes break, okay? We're going to start at 3:35 instead of 3:30 as scheduled. Good. So, Chaco, I made you a co-host, so you can try to share your screen, just to make sure things are working.
Yeah, let me try that.